Hello everybody, Ian King again, going through the lecture notes for Economics 2020 Macroeconomic Theory. So we're starting today with topic number 1, where we're going to be looking at really three subtopics. An introduction, just a brief introduction to the course. Secondly, we'll talk a little bit about national account identities, and then we'll get on to the basic Keynesian model, which is also known as the Keynesian cross model. Okay, we'll start with a very basic introduction and a basic question that I think should always be asked in a course like this. What is it that we're trying to do? What is macroeconomics? Well, there's lots of different theories, or different definitions that you can find for macroeconomics. But the one that I found that's particularly relevant and meaningful is by Richard Lipsey, who's a famous economist. And it's about, he describes it as the study of the determination of economic aggregates. So really what causes economic aggregates like output, unemployment, inflation, and so on. So I don't expect you to memorize this definition, but I think it's a good place to start. Just conceptually, we're trying to explain things using theories and models. So there are really two questions that motivate macroeconomics for the most part. So first of all, what causes recessions? And what causes growth, inflation, unemployment, changes in the interest rate, exchange rates, and so on? These are all macroeconomic variables. What causes them to change? And secondly, what role can policy, in particular government policy, play to improve macroeconomic outcomes so that we're in a better world than we'd be otherwise? So these are, I say, the two essential questions that are driving macroeconomic analysis. So the purpose of this course is to familiarize students with the central concepts and the theories and tools that are at the heart of macroeconomic analysis. It's fairly standard material in this course. We try to provide you an understanding of what we think of as being the sort of core canonical theory and models of macroeconomics. So for the most part, we'll be focusing on these theories and the models that embody these theories. So what's the difference between a theory and a model? Well, a model is really a mathematical representation of a theory. And will be the nice thing about that is you can use these models to actually quantify, put numbers to what we expect to happen to the economy in response to economic shocks. For example, whenever there's a major event like, let's say, a stock market crash, or perhaps some major policy change by a politician in a powerful country, economic policy that hopefully is designed to make things better. But first of all, before we get into the theory, it's useful to look at some truths that we can get really for any macroeconomy, regardless of what theory you actually believe. So what I mean by that is really the national accounting identities, which I believe everybody here has seen before in their first course in macroeconomics. So I'm going to I don't want to go too deeply into national accounts, but I just want to point out one or two things that are interesting from the national accounts. So first of all, some notation. All right, capital Y is aggregate output, or gross domestic product, GDP, which is also national income. Capital C is aggregate consumption on expenditure and goods and services, so what we consume. IA is actual investment expenditure. This word actual is actually quite important, and I'll talk in more detail in a few moments about that. G stands for government expenditure on goods and services. TA is taxes, and TR is transfers. So taxes raised by the government and transfers paid by the government. Capital S is private savings. X, capital X, is foreign expenditures on our exports, goods and services. So foreigners spending on our goods. And IM stands for domestic expenditure, so our expenditure on imported goods and services from overseas. Now, you may recall from your first year economics course, the national accounting identities can be expressed in two different ways. First of all, what's called the expenditure side identity, and I'm going to call this equation 1.1. Now, throughout these notes, I'm going to try to number these equations to keep it easy to refer to them, back to them when we need to. So the expenditure side identity, which I believe everybody has seen before, is that GDP is equal to consumption expenditure plus actual investment expenditure plus government expenditure plus exports minus imports. And the income side identity really looks at, rather than the components of expenditure, it looks at what you can do with your income. So capital Y also represents income, and it can be divided up into consumption or savings or taxes minus transfers, what are known as net taxes. So capital T is defined as being taxes minus transfers. So this I'm numbering equation 1.2, that's the income side identity. Okay, so these are two equations that hold for all economies for all time. No matter what you believe, this holds just by definition. Now, what we can do is bring these two identities together. So you'll notice, of course, they both have y on the left-hand side. So what I'm going to do is I'm going to substitute out this y. I'm going to bring this side of equation 1.2 and substitute it over here into equation 1.1. And we get the following result. Here we go. At the top, there's y is equal to c plus s plus taxes minus transfers. So that's the income side of the identity. And on the right-hand side, the expenditure side is equal to c plus ia plus g plus x minus im. Okay, now if we look at this equation for a moment, we can see that we've got c on both sides, which will just cancel out. And I'm going to collect terms. On the left-hand side of this equation, I'm going to keep savings, S, and I'm going to bring investment over to this side. Of course, it's going to take a minus sign when I do that. And then I'm going to throw everything else on the right-hand side. So just rearranging, we get on the left-hand side, S minus IA, which is known as private net savings. And that's equal to G plus TR plus TA, so government expenditure plus transfers minus taxes. This is what's known as the primary government budget deficit, plus X minus IM, the trade surplus. Okay, so that's, again, just a reminder. Now we're going to call this equation 1.3. A reminder is that this holds for all economies for all time, whether you are a Keynesian or a classical or a Marxist, no matter what you believe, you have to also believe in this, this equation. Okay, so what is it telling us? It does tell us a few things. First of all, suppose private net savings is zero. I mean, suppose savings and actual investment are exactly the same amount. So we've got zero on the left-hand side of this equation. Then that must mean that the government's primary government budget deficit is equal to minus this. So minus the trade surplus, which is also known as the trade deficit. So this is saying that if private net savings is zero, then the trade deficit will be equal to the government's primary government budget deficit. Now, actually, this is a little more general. Suppose that private net savings is fixed at any number. Could be 0, could be 100, could be any number. But if it's fixed, if it doesn't change, then any increase in the government's primary government budget deficit will increase the trade deficit by the same amount. So just by the basic math of that equation, it says if you hold this fixed and you increase this, then this must go down, which means the trade deficit must go up. So you often hear in the media this discussion about twin deficits, the government budget deficit and the trade deficit. And that's really what they're referring to. So there's quite a bit of discussion about how if you increase the government budget deficit, well, then it's going to increase the trade deficit. But also, we could interpret this differently. If the trade deficit is fixed, I'll just go back to that equation again. Suppose the trade deficit is fixed, or the trade surplus is fixed, then any increase in the primary budget deficit will necessarily increase private net savings. Again, looking at this equation, if we hold this fixed and we increase this, then it must be that this goes up as well. So an increase in the primary government budget deficit will actually increase private net savings according to this equation. I'm going to look at one more variation on this equation. Suppose the trade surplus is fixed, and suppose private savings is fixed. Then any increase in actual investment will reduce the primary government budget deficit. Let's take a look at that. So we're saying if savings is fixed and the trade surplus is fixed, then any change in this will be reflected in a change in this. So that's just another variation on what we can get out of this equation. We can tell many stories like this. So we can fix some variables and change others, and that equation will then say, well, it must be the case then that this other thing changes. So, but which one is right? We told 4 different stories here, but which one is the relevant story? How do we know which variables to fix and which to remain, which we can change to change things? So in order to answer that question, we really need to have a theory of causation. What causes what? And this is really where macroeconomic theory comes in. Now, before we get right into the mathematical theory of macroeconomics, let's just briefly touch on some concepts, theoretical concepts that are true for any theory. First of all, and when I say any theory, I mean in any field of inquiry, economics or physics or sociology or any science that has any theories in it, in principle, has these basic ingredients. First of all, a model, as I mentioned before, is a mathematical representation of a theory. It's a very explicit formulation of the theory. Now, an endogenous variable is a variable that is actually being determined or explained by the theory itself. So, for example, a classic endogenous variable in macro models is output. So it's something that the theory is explaining output. By way of contrast, an exogenous variable is a variable that is not determined by the theory itself. It can be an important variable, but it's not being determined by your theory. It's determined somehow outside of your theory. Now, so you think of these things as being fixed. They're not although they can actually be changed from policy and so on, but they're not actually being determined within the model. And a parameter is another fixed thing. It's a fixed number. It's not a variable, though, and it's not being determined by the theory. So actually, maybe just quickly, an example of an exogenous variable is often we think of government expenditure as an exogenous variable. So this thing changes really according to the initiatives and desires of politicians, rather than by necessarily the macroeconomy itself. An example of a parameter would be something like, we'll see people respond to certain things in the economy. For example, as income goes up, most people will actually consume more. And the amount that they consume depends on their preferences. And we typically think of preferences as being sovereign, which means here that there are certain parameters that don't change. Now, so both exogenous variables and parameters in any theory are taken as givens in the theory itself. And you'll see in the examples I give you, and for example, the assignment, there'll be particular numbers for the exogenous variables and parameters. And then you have to work out the endogenous variables, in particular output, but other variables as well, as a function of those exogenous variables and parameters. All right, a little bit more. A closed form expression of an endogenous variable is a way where the expresses that variable, the endogenous variable, in terms only of the parameters and exogenous variables in the theory. So once we find a closed form solution for an endogenous variable, that's what we mean by the solution of the for that variable. So this will become much clearer when we get into the context of a particular model and also numerical versions of it. So, but in general, any theory, and again in any science, can be broken into its component parts: endogenous variables, exogenous variables, and parameters. So if you're ever in a lecture by someone or a talk by a politician or whoever is trying to put forward a theory, it's usually and often a good idea to think about, well, what's endogenous here and what's exogenous and what's a parameter. And maybe you could actually ask the person who's presenting the lecture, say, what is it that's endogenous in the model, and what's being held fixed exogenously, and what's a parameter in the model? And now, if they cannot really answer that question clearly, then I would argue they don't really know what they're talking about. So in this course, I will try to be as absolutely clear as possible about what's endogenous, what's exogenous, and what's a parameter. Okay, now in this course, we're actually going to look at several different theories. And each of these theories will have some endogenous variables, some exogenous variables, and parameters. And now in macroeconomics, most standard textbooks follow the lead of a very famous macroeconomist by the name of John Maynard Keynes. So some would argue that actually macroeconomics actually began with John Maynard Keynes with the publication of his book, The General Theory of Employment, Interest, and Money in 1936. So he was incredibly influential, and arguably that was the birth of modern macroeconomics. Now there's no required textbook for this course, as I mentioned before when I talked about the course outline, but there are two recommended textbooks, the one by Dornbush, Bodman, Fisher, and Startz, and the one by Blanchard and Sheen. So again, you don't need to buy those textbooks for this course, but both of these textbooks can be used as useful background reading, and they both follow this tradition of keeping Keynesian analysis really at the heart of most of what goes on in the theory in the book. Now, at the heart of Keynesian analysis, So what does it mean, Keynesian theory? Well, actually there's huge debates about what it really means, but most people would agree that really at the heart of Keynesian analysis are two key assumptions or presumptions. First of all, that prices might take some time to adjust. If there's some change in the economy, prices don't adjust instantaneously. Now, when I say prices, we mean prices of everything, but including wages. So wages, of course, are the price of labor. And this is an extremely important price. And arguably arguably wages do take some time to adjust. I know, for example, my own contract with the University of Queensland, we negotiate a wage from year to year, but over the period of the year, my wage is fixed. And so if there's some change to the economy, some inflation or any other change in the economy, my wage is fixed over that period. And so it's not really a very extreme assumption to presume that wages can actually be fixed for some period of time. Also, another key presumption is that there can be times when actual expenditures in the economy are not the same as the planned expenditures. So these two presumptions, as we'll see, can have really, really significant impact on how an economy behaves and how it responds to when the government tries to do things with policy initiatives. And we'll also see that this is a really radical departure from what existed before Keynes's time, what's known as the classical understanding of macroeconomics. So we will spend some time in this course actually looking at what's known as the classical model as a contrast to the Keynesian model. So these days, most macroeconomists agree that it sort of makes sense to break down the effects of any change in the economy into three essential time horizons. First of all, the short run, then the long run, and then the very long run. So in the short run, three things are held constant that are very important. First of all, prices. Secondly, capital, the amount of capital in the economy. And third, the level of technology in the economy. So those are held fixed. But what's allowed to change endogenously are output, employment, and interest rates, those three key variables. Now, as you move for a longer run into what's known as the long run, once again, the level of capital and technology are fixed. So two things are fixed now. But prices are allowed to vary. So prices, output, employment, and interest rates are now adjustable in the long run. Then there's the very long run, where essentially everything can change. In particular, capital and technology are allowed to change in the very long run. So in this course, as is standard in most macro courses, we'll start with the short run, and then we'll proceed on to the long run, and then we'll end off with the very long run. We're also going to start off with the very simplest possible macro model. It's known as the Keynesian cross model. So the model is very simple, and it's intentionally very simple. It abstracts away from many, interesting and important issues, like a lot of issues that actually will be covered in later sections in the course. But the point is here, I want you to be able to solve simple models. We start with simple models, and once you master solving those, we'll move on to more complicated models, and you hopefully will be able to solve those too. And as we walk through the course, by the by the end of the course, you should be able to solve some pretty complicated models, having really invested your time in learning how to solve first these simple models. But also, I will say that this first model we look at is an interesting model. It really clearly demonstrates some of the key mechanisms and the power of Keynesian analysis. So this is a Keynesian model, and you'll see how, in particular, government policy plays a really important role in a model like this. Okay, so let's get started with Model 1, the Keynesian cross model. And we're going to start with a new concept, the concept of planned aggregate expenditure. It's sometimes called the total demand for goods. And we're going to denote it by the capital Z. So that's planned aggregate expenditure or total demand of goods. Now, conceptually, what this is it measures the total amount that domestic residents in a country or in an economy intend to spend. So it has components that are similar to what we had previously when we were talking about national income accounts, but there's a crucial difference, and it's all about investment expenditure. So usually macroeconomists, and here certainly in this course, macroeconomists presume that expenditures on consumption and government expenditure and net exports are actually exactly what people plan them to be. However, investment expenditure is different. It has a key component that doesn't always correspond exactly to what was planned, and this is what's known as inventory investment. So firms have inventories of the goods that they're trying to sell. Now, in national accounts, whenever you have an increase in inventory, it has to be counted as something. It has to go somewhere in the national accounts. And the way where it's put in the national accounts is it's considered to be a type of investment. So if a firm produces a bunch of shoes, let's say, and then puts them in a warehouse, stores them, that's inventory that's stored, and it's counted as investment. Now, of course, many firms plan to carry some inventories because really it's good to have some inventories there because you never really know. Demand goes up and down for your good, and it's good to have a buffer stock of the good available for whether, for example, when demand's really strong. So actually, on a personal note, I actually used to work in a carpet factory many years ago. And we used to have an inventory of carpets that would go up and down depending on how the orders came in. However, sometimes firms find that their inventories change in ways they weren't expecting. So if, for example, not many orders come into the carpet factory, if the demand for their good is unexpectedly low, they find that they're grinding away, producing these carpets, and their inventories are accumulating in a way they weren't expecting. And sometimes the demand's really good, so that lots of contracts come in, and they find that their inventories actually decumulate in a way they weren't expecting. So if you look at the warehouse, you'll find that suddenly we're actually running out of carpets in a way that weren't expected. Now, so firms can be subject to what's known as unintended inventory investment. So this can be either negative or positive. If it's positive, they find their inventories are accumulating in a way they weren't expecting. And if it's negative, then their inventories are decumulating. So this means that actual investment can be different from planned investment, because actual investment includes this volatile, unintended inventory accumulation, whereas planned investment typically does not include that. So a little bit more notation. Let I, capital I, be planned investment expenditure, and I with the subscript U be unplanned investment expenditure, by which we mean unplanned inventory accumulation. So we have another equation, 1.4, which is that actual inventory investment is equal to planned Actual investment is equal to planned investment plus unplanned investment. Now, planned aggregate expenditure has these components. So again, we're using this Z for planned aggregate expenditure. It's consumption expenditure and planned investment expenditure, government expenditure, exports minus imports. So let's just contrast this with GDP in the national accounts above, equation 1.1. We saw that y is equal to c plus IA plus g plus x. So the difference between these two is really the i's. In this case, planned investment expenditure, and in this case, actual investment expenditure. Now, for the next few lectures, we're going to be looking at what are called closed economies, economies that are isolated. They're not trading with other economies. Now, this is mainly, this is the way that most macroeconomics textbooks deal with going through these issues. It's also for pedagogical reasons. It keeps it simple, first of all, to look at a closed economy. But it's also interesting to look at closed economies in their own right. So the world as a whole is a closed economy. Also, actually just historically, it was the case that when I was a student, it was said that an economy with less than 10% of GDP in trade was called a closed economy. And the US economy was considered, therefore, to be actually, at that time, a closed economy, because it was mostly trading with itself. So a lot of textbooks, of course, have been written by famous American economists, and so that's historically why we typically start with closed economies as a starting point. Now, when the economy is closed, that means that exports are zero and imports are zero. So in that case, planned aggregate expenditure is just C plus I plus G. So now what we're going to do is we're going to look at, so we're going to take this equation and we're going to consider different theories of C and I and G, which is each of them are planned consumption, investment, and government expenditure. We're going to start with consumption expenditure, it's big C. And actually, consumption expenditure in most economies is actually the largest component by far. So most of aggregate expenditure is consumption. So we're going to be looking at what's called a consumption function, and its twin, a savings function. You'll see how these two are connected. So a key decision that consumers must make in any macroeconomy is how to divide up their income between consumption and savings. So you get your income at the end of your pay period, and you have to decide how much of it I'm going to consume now and how much I'm going to save. So just a little bit more notation to hopefully make it easier. Let Y subscript D be consumers' after-tax income, or what's known as disposable income. So YD in this model is output, Y, minus taxes, plus transfers. Now I'm going to just use a little bit more notation, again with the hope to minimize notation. So let's use this big capital T as taxes minus transfers. You can think of that as net taxes. Therefore, disposable income is equal to income minus net taxes. And consumers have to choose how much to consume and save, subject to a basic constraint. Your consumption plus your savings has to add up to whatever disposable income you have. In this context, well, so in general, when thinking about consumption and savings decision, it's really a dynamic problem. So people considering, well, if I'm going to be working for so many years and I may retire, let's say several decades from now, and I want to save in order to finance my retirement, and I need to think about interest rates now and future interest rates and so on. So it's in general a fairly complicated dynamic problem. And if you go on into future courses in economics and macroeconomics, you'll actually spend quite a bit of time thinking about this dynamic problem of consumption and savings. However, In this course, we're going to be using a simple static model, at least to begin with. And we're just going to, following textbooks and following the way it's typically done, we just assume that both consumption and savings are just functions of disposable income. So C as a function of disposable income and savings as a function of disposable income. These functions are in general, what they're known as is behavioral functions. So we're not actually going to be analyzing specifically the microeconomics behind people making their decisions. We're just going to presume that people actually have these parameters in their heads where they just use these simple rules about how much they're going to consume and how much they're going to save out of their disposable income. So first of all, we're going to assume that their both consumption and savings are an increasing function of income. So the more you have, the more you consume, and the more you save. Now, we're going to, for the next few lectures, we're going to be presuming that there's a simple linear consumption function. So consumption is equal to some constant parameter, C0, where C0 is, here I'm using the notation, C is positive, C0 is positive, which means it's just a positive parameter. So some number, maybe 5. Plus C1 times disposable income. Now C1 is assumed to be between 0 and 1. That's what this notation means. It's a little bit fancy, I suppose, the way it's written. It just, this is saying that C1 is an element of the interval 0, 1. So it could be, for example, 0.5 or 0.8 or 0.1111, 0.999. They're all allowed, but not 0 and not 1. Okay. So a standard parameter value is, for example, 0.8 for C1. So C0 is known as autonomous consumption, which is sort of fixed, and C1 is seen as called the marginal propensity to consume. This really comes out of the language of Keynes, who was English, and that's the sort of the way that English people used to speak back in his day. Okay, now let's just do a little graph of the consumption function. So on this axis, I've got YD, disposable income, and this axis, consumption. So, and here I've got the equation for the consumption function. C is equal to the autonomous component, C0, plus the marginal propensity to consume, C1 times YD. So the intercept on the consumption function is C0. If income is 0, like back here, then people are still able to consume some amount, C0. Maybe they run down their savings, or they borrow from friends, or from somewhere they find some way to consume. So that's what consumption is if income is 0, but as income increases, consumption also increases. But it increases by less than 1. So the slope of this consumption function, C1, we said is less than 1. So it's not at a 45-degree angle. It's a little bit less than a 45-degree angle. Now, I'm actually, for most of the course, I'm going to rewrite this a little bit so that we can graph this in terms of y instead of yd. So what I'm going to do is I'm going to take that consumption function and go back here and just take this consumption function, and I'm going to substitute in our definition for yd, which you remember is y minus t. So let's do that. So if you put in, you substitute that in, you'll get this. C0 is equal to minus C1t plus C1 times y. So now I have on this axis income, not disposable income, but income. Same thing on this axis, consumption, same as it was. But now the intercept on the consumption function it has two components, C0 minus C1t. And that's what we got here. But the slope remains the same. It's equal to C1. So this is our induced component of consumption. So as income increases, consumption increases along this line. Okay. Now, whenever we specify a consumption function, it means that we automatically specify a savings function as a byproduct. So remember that consumption plus savings equals disposable income. So therefore, once you have specified consumption, then given disposable income, you're also specifying savings. That's whatever you didn't consume. So let's go back. Remember that we had consumption plus savings sums up to disposable income. So that was equation 1.7. Now we're going to substitute in our particular consumption function into that equation. So we get C0 plus C1yd plus S is equal to yd. Okay, now I'm just going to solve this equation for savings. So keep savings on the left-hand side, throw everything else on the right-hand side, collect terms, and you get this. Savings is equal to minus C0 plus 1 minus C1 times yd, disposable income. This is what's known as the savings function. Okay, I'm calling that equation 1.10. Now notice the savings function has the same parameters in it as the consumption function, C1 and C0. But they have different interpretations here. So just go back and just look at that savings function again. So this is the intercept of the savings function, and this is the slope of the savings function. So minus C0 can be thought of as autonomous savings, as minus autonomous consumption. And the term 1 minus C1 can be thought of as the marginal propensity to save, which is just 1 minus the marginal propensity to consume. Now once again, we can express this savings function slightly differently by putting it in terms of y rather than yd. So by substituting, let's maybe just go back again to that equation, back to this equation we had before. We got yd here, but I'm now going to substitute in our definition of yd to get things in terms of y. So let's do that. And you get this equation here. Savings is equal to minus C0 minus 1 minus C1t plus 1 minus C1 times y. I'm calling that equation 111. So I invite you to do that substitution and make sure that that is correct. Here's what the savings function looks like when we've got y on this axis and functions of y in general on this axis. So notice I've drawn this here where this is the axis. We've got positive values of y. But actually for savings, it's possible to have positive values or negative values. So this axis here allows for both positive or negative values of savings. Now when income is 0, just for a point of reference, then we can see that savings is just equal to minus C0 minus 1 minus C1 times t, which is the intercept now of the savings function. So in that case, there's negative savings. It means that people are actually not saving in this period, they're actually running down their savings. So, okay, but as income increases, people save more, and then eventually you get to a point where people are just saving 0, which means their consumption is exactly equal to their income. So it's sort of hand-to-mouth living. Now, if income increases beyond that point, then they're actually doing some positive savings. So that's our theory of consumption and savings. Now, let's talk about investment. Remember, we've got, in our equation, we've got y is equal to c plus I plus g. We're walking our way through each of these terms. We did C, now we're going to do I, planned investment. Well, investment theory is also, there's a huge literature on investment theory, and it goes way back. It can be quite complicated. In general, it's a dynamic problem again, because firms, whenever you invest, you're paying an amount now for payoffs that are going to come in the future. So you're comparing sort of current costs versus future benefits. And whenever you do something like that, you really have to do what's called a present value analysis. You have to compare the expected present discounted value of the benefits from the project with their costs. So as mentioned before, costs are paid mostly up front, while benefits occur mostly in the future. Now, in the tutorial, we're actually going to go through a bit of a review, hopefully, on present value analysis, and how you'll see that as interest rates go up, that reduces the present value of any project. So any increase in interest rates reduces the expected present value of benefits more than the expected present value of the costs, because costs tend to be up front. So therefore, this reduces the attractiveness of investment projects. So investment tends to go down as interest rates go up. So we will explore that issue further below. We'll look at these present values. However, for the moment, we're going to look at a very, very simple Keynesian cross model, where investment is actually just given. This is a very simplistic theory of investment. And again, we will relax that, and we'll have more general theories as we go to more sophisticated models. But for the moment, we're just going to say, suppose investment is just given as an exogenous variable. So I is equal to I bar. So whenever I put a bar over a variable, usually what I mean by that, always what I mean by that, is that it's fixed. So I bar is some positive or at least non-negative value. Okay, so we've looked at C and we've looked at I. Now let's look at the last component of planned aggregate expenditure, government expenditure. Now, as I mentioned before, economists tend to think of government expenditure as something that's really, really hard to predict. It's really up to the whims of politicians, and sometimes politicians can be quite unpredictable. So for this reason, G is usually modeled just as an exogenous variable. G is equal to G bar. I'll say this is true even in sophisticated macro models. So if you ever go on to look at a really frontier macro theory that's in the top macroeconomics journals, typically they'll think of government expenditure as being exogenous. Okay. However, tax systems usually are treated in a more sophisticated way. So in this model, however, we're going to assume that there's some fixed amount of net taxes given exogenously, T bar. Now, again, actually this will be relaxed. In particular, it will be relaxed in your assignment, in the first assignment. Now, governments themselves face budget constraints. These are known as government budget constraints. And they face these constraints at least in expected present value terms. Now, we say that a government has a deficit whenever government expenditure is greater than taxation, net taxation. So they're spending more than they're taking in. They say they have a balanced budget if G is exactly equal to T. That's what a balanced budget means. And then they have a surplus if what they're raising through net taxes is actually greater than what they're spending in government expenditure. So that's just a definition of those terms. Now, of course, this, when we start talking about these deficits and surpluses, this has immediate implications for government debt, which is another dynamic and important issue. There's a lot of debate around this. We'll touch on this later in the course. But for the moment, we're going to put those dynamic effects aside and just look at the simple static model that is the Keynesian cross model. All right. Now, let's just talk a little bit about demand supply. We've just finished specifying the behavior behind all of those components, C and I and G, for the demand for the goods. What about supply? Now, in this really, really simple Keynesian cross model, it's assumed that firms are very, very simplistic. They just supply whatever is demanded at the same fixed price. Now, you may say, well, that's not very reasonable. And, well, this gets again to the sort of heart of Keynesian analysis. And we will, later in the course, we're going to relax that assumption. We're going to look much more closely at firms, when firms can actually change their prices. But for the moment, we're following standard practice, and we're just going to say, in the short run, prices are fixed. So therefore, outcomes are actually determined purely by demand. Firms just passively produce whatever is demanded at that price. Again, it's extreme, but we will relax it later on. Okay, so now looked at demand and supply, and whenever demand and supply come together, we have something called equilibrium. In this simple model of the goods market, the equilibrium condition is that actual aggregate expenditure is equal to planned aggregate expenditure. So remember, actual aggregate expenditure is Y, and that's equal to planned aggregate expenditure, Z. This is the last condition we need to solve the model. So we now actually have enough equations so that we can sit down and just mathematically derive the solution to this model, and thereby our prediction for what equilibrium income and consumption and savings are going to be. Before we do that, though, I think it's useful to just collect together all of the key equations we have. So they've been spread over 30-odd slides, and let's just collect together a summary of the key equations that we need to solve the model. Here we go. So I'm just using the same numbering system as we had before. We'll start with the equilibrium condition. Y is equal to Z. So actual expenditure is equal to planned expenditure in equilibrium, only in equilibrium. Then we've got the components of planned aggregate expenditure. Z is equal to C plus I plus G. And we have the consumption function, our theory of consumption, which we had before. Our theory of investment, super simple. It's just exogenous I bar. Our theory of government expenditure, super simple as well. We set it equal to G bar. And then our expression, our theory of taxes in this very simple model, T is equal to T bar. Okay, that's our model. So how do we solve this model? Well, let me just tell you, before we get into it, let me just give you the method. We always start with the equilibrium condition. And then we substitute this into the equilibrium condition. So we get rid of Z, and we'll end up with Y is equal to C plus I plus G. And then what we're going to be doing is we're going to be substituting in our different theories. The theory for C, the theory for I, and the theory for G. We'll also need a theory of taxes as well, because that's a component of consumption. So let's do that. That's the way it works. You take the equilibrium condition, substitute this in, and then plug in all your theories, and you'll find then you get one equation in output, and you solve for that value of output. Let's do it. Oh, but before we do it, let's just break down the model. Again, I keep saying that every theory has endogenous variables, exogenous variables, and parameters. Let's just summarize what those are in this model. Here we have really 4 endogenous variables: output, planned expenditure, consumption, and savings. And we've got exogenous variables I bar, G bar, and T bar. So investment, government expenditure, and taxes. And we have 2 parameters: the autonomous component of consumption and the marginal propensity to consume. So when we say we're going to solve the model, what we mean is we're going to express the endogenous variables solely in terms of exogenous variables and parameters. Okay, now let's do it. As I said before, we're going to take y is equal to z, and we're just going to substitute in z. So in this case, z is equal to c plus I plus g. And we got those behavioral functions, one for consumption, one for investment, and one for government expenditure. So let's just substitute them in. So our theory for consumption expenditure is it's equal to C0 minus C1 T bar plus C1 times Y. Our theory for investment expenditure is just equal to I bar. And our theory for government expenditure is just equal to G bar. Well, okay. Now if we look at this equation now, it's one equation in only one unknown. The unknown is Y. It's here and here. So let's collect terms. Maybe just an intermediate step. Let's just take this C1Y and take it over to the left-hand side. It's going to become minus C1Y. So we'll have Y minus C1Y on the left-hand side. And then we just divide through by 1 minus C1. And we're done. This is it. This is our equilibrium GDP in this model. I'm going to call it Y star. So I'm going to put an asterisk on it, or I'm going to call it a star. And this tells us this is the equilibrium value of output as a function of all of the exogenous variables, T bar, G bar, and I bar, and the parameters C0 and C1. So that's our equilibrium GDP in this model. This will become a bit clearer when I actually put in some numbers for the exogenous variables and parameters. But for now, you can see that we've expressed the endogenous variable y only in terms of exogenous variables and parameters. Now, once we've found y star, it's easy to find the equilibrium values for all the other endogenous variables. Let's start with z, planned expenditure. Well, z is equal to y, so therefore z star is equal to y star. So this same expression is equilibrium planned expenditure. Now, substituting, now let's get C. Let's get C star. So we take C star is equal to C0 minus C1 T bar plus C1 times Y star. And now we know what Y star is. We'll plug that in there. We get this. Let's just collect terms a little bit. And we get this. C star is equal to, again, we've expressed it solely in terms of exogenous variables and parameters. That's equilibrium consumption. And then now we can also get savings. So we had our savings function is, we had S is equal to minus C0 plus 1 minus C1 T bar plus 1 minus C1 times we had Y. Well, now in equilibrium, S star is equal to this times Y star, which is this. We've already solved. So plugging that in there and then collecting terms after a little bit of mathematical magic, we get this expression. Equilibrium savings is equal to planned investment, government expenditure minus taxes. Now let's do a numerical example. So we've got two parameters, C0 and C1. Let's set C0 equal to 5. So imagine, for example, the way that economists, macroeconomists do this is they go out with, they look at data for a macroeconomy, and they use statistical techniques called econometrics, and they use those techniques to get an estimate of what C0 is and what C1 is. And so C0, we're going to use the number 5, which is sort of a standard number, and then C1 is 0.8, another standard number. And also you can get estimates for how much investment is going on. So think of this maybe as being in units of billions of dollars, for example. So $2 billion worth of investment, some government expenditure, $1 billion, and then some taxes, net taxes, $1 billion also. Then if we take these numbers and we plug them into the solutions, so back there we had y star, you plug in the numbers for C1, C0, and these guys, you should get, and I invite you to do this, please do this at home, plug in those numbers and verify that you get y star is equal to 36, which of course means z star is equal to 36. So that's actually going back, maybe just being a little bit pedantic about it, but if we go back here, here's our y star. That's equation 1.16. If you plug in our values like 5 here, 0.8, and all of the numbers for t bar, I bar, and g bar, you should get that number 36. And if you do it for consumption, we have an expression for consumption also, just up a little bit. There it is, equation 1.18. Plug in the numbers to that and you'll get C star is equal to 33, which is less than Y star, but again, C star is the major component of consumption, of planned aggregate expenditure. Now, savings is equal to, again, plug the numbers in and you'll get 2. All right. Now, diagrammatically, let's look at how this works. Again, we've got our output on this axis, and we've got, in general, functions of output on this axis. I've put Z here really to denote expenditure, planned aggregate expenditure. Now, I'm going to start with something that we know, which is the consumption function. So remember, the consumption function has an intercept, C0 minus C1 t bar, and then it has a slope of little c, the marginal propensity to consume. So it looks like this, as before, exactly as before. But now, aggregate expenditure has consumption as a component, but it has other ingredients as well. So aggregate expenditure, Z, is equal to consumption plus I bar plus G bar. So it's going to have intercept. It's going to be the consumption plus some fixed extra terms, I bar plus G bar. So it's going to have a bigger intercept. But the slope is the same. The slope is just the marginal propensity to consume, C1. So this is our aggregate expenditure function. Okay, so it lies everywhere above the consumption function, but it has the same slope. Now, there's another line on this diagram. This is Z is equal to Y. Remember, that's our equilibrium condition. Whoops. There we go. That's our equilibrium condition. So, whenever graphically, our equilibrium is where the planned aggregate expenditure function is equal to the equilibrium line. So we get Z is equal to Y at this point, or Y is equal to Z, and Z is equal to this planned aggregate expenditure function. So where these two intersect, that's our equilibrium. This tells us what Y star is here and what Z star is here. Okay. And actually, once we know what Y star is, then we can actually just follow this dotted line here, and this will tell us what C star is, how much consumption expenditure happens in equilibrium. So we could draw a little dotted line over here, and this will tell us C star. I didn't do that just to try to keep the diagram visually simple, but you could do that. Okay. Now, let's look at some comparative statics in this model. So really, a lot of what economics is about, macroeconomics, is how can we use policy to change things? And how is the economy going to be kicked around by, exogenous good or bad events? So to answer this question, I'm going to remember our expression for equilibrium output, Y star. It was all of these guys, C0 minus C1 T bar plus I bar plus G bar. That's what's known as autonomous spending. and then it was divided by 1 minus c. I'm just rewriting this slightly. I'm factoring out this 1 over 1 minus c1 here and keeping this as in brackets. These are all the components of autonomous spending. Now I've used this word multiplier here. So when I say multiplier, I mean this whole thing. 1 over 1 minus c is known as the multiplier in this model. And that what it means is any change in any of the autonomous components, so for example, suppose we increased I bar, that's going to obviously have an effect on y star. But the effect it has depends on the size of this 1 over 1 minus c1, the multiplier. Okay, and similarly for all the other terms. Now, you remember, we did this little mathematical review right at the beginning of the class, and we said whenever we have a linear equation with some variables on the right-hand side and some parameters, then with this, this is a linear equation. I got this here times all of this. These are all linear. Right? There's no squared terms or cubic terms or anything like that. They're just simple linear equations. So we can go from this equation and we can jump right to this equation. It says the change in y star is equal to the multiplier, 1 over 1 minus c, times the change in c0 minus c1 times the multiplier 1 minus c1 times change in t bar times 1 over 1 minus c, the multiplier again, times change in I bar times 1 over 1 minus c1, again, the multiplier times change in g bar. So just going back, whoops. Pardon me. So going back to this equation, we can see that it's all linear, so we'll get like change in y star is equal to this times change in c0 times c1 times change in t, and so on. That's what we're doing. So this is a very handy equation. It tells us how equilibrium y changes as we change any of these variables. So let's consider some specific examples. And we'll end off with an example of expansionary fiscal policy, a very classic example. So suppose government expenditure increases as a positive change in G bar, but none of the other exogenous variables or parameters change. So change in C0 is equal to 0, change in I bar is equal to 0, change in T bar is equal to 0. So let's just go back and look at that equation we had before, this equation here. We're setting this equal to 0, we're setting this equal to 0, we're setting this equal to 0. So all these terms are going to be 0, right? And we're left only with 1 over 1 minus C1 times change in G bar, which is the equation we're going to look at here. Okay, so this says if those other guys don't change, a positive change in G bar is going to cause a positive change in equilibrium output, y star, which is equal to 1 over 1 minus C1 times that change in G bar. Okay, let's use the numbers that we were looking at before. So for example, if C1 is equal to 0.8, then 1 minus C1 is equal to 0.2, which is so therefore 1 over this, 1 over 0.2 is equal to 5. This is saying that change in y star, in that example, when C1 is equal to 0.8, change in y star is equal to 5 change in G bar. So it's saying if you increase government expenditure by $1 billion, then equilibrium output increases by $5 billion. So this is actually a remarkable result. It may seem magical. How is it possible that you can increase, if you increase government expenditure by $1 billion, the economy expands by $5 billion? That seems wonderful, but also quite mysterious. And the answer, why do we get this result? And the answer lies in the fact that consumption is a function of income. So if we get any increase in any of the autonomous components in expenditure, for example, government expenditure, if that goes up, then, well, because government expenditure is a component of aggregate expenditure, y is equal to c plus I plus g. If g goes up, then y goes up for sure. But when y goes up, remember that consumption is a function of y. So as y goes up, then c goes up. But c is also a component of aggregate expenditure. So as c goes up, y goes up again. And so as y goes up again, then c goes up again. So y goes up again, c goes up. We go these successive rounds. So an initial increase in g has initial impact, but then that causes a ripple effect of subsequent rounds of consumption. So this is just walking through this mathematically now. For example, since G bar is a component of Y, a $1 billion increase in G bar causes an immediate increase in Y by the same amount. So in the first round, as G bar goes up, government expenditure goes up, then output goes up by also $1 billion. But because Y has gone up by $1 billion, we know that consumption will increase by this amount, this marginal propensity to consume times change in Y bar, which is equal to this change in Y bar is equal to change in G bar. So we get, now since C is a component of Y, that increment of C means that's going to cause another increase in Y. And so in the second round we get this. And now Y is increased by this additional amount, and again that increases consumption by an additional amount. And again, it's now going to be C1 times this new change in output. So it's going to be C1 times C1 times change in G, or C1 squared times change in G. Now that's another increase in consumption causes another increase in output. So that's going to give us a third round increment in output, C1 squared times change in G. And then there'll be a fourth round. We'll get C1 cubed times change in G. A fifth round, change in Y is equal to C1 raised to the fourth power cubed times, not cubed, but to the fourth power times change in G. And this process actually continues indefinitely to the fifth power, sixth power, seventh power, 100th power. So that sounds like, well, this is just going to go on forever, like output will just keep increasing. But the thing is that with each new round, the increment you get in Y is a bit smaller than the previous round, due to the fact that the marginal propensity to consume is, remember, C1 is less than 1. So with every round of increase in income, a little bit gets shaved off out of consumption and actually into savings. So if we add up all the increments to Y, you get that first round increment, second round, third round, so on. And we can just factor out this change in G bar, and you get change in Y star is equal to change in G bar times 1 plus C1 squared plus C1 cubed, and so on. Now this thing, 1 plus C1 blah, 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 is an example of what's called a geometric series. Now, if you go and you look in those mathematical notes that I circulated, you'll see geometric series, very commonly used series, and they have very nice properties. In particular, you can show that when you've got, if C1 is strictly between 0 and 1, a fraction, then 1 plus C1 squared plus C1 cubed, going on forever, actually is equal to 1 over 1 minus C1, which gives us our result again, that the change in equilibrium Y is going to be equal to all of those guys summarized in 1 over 1 minus C1 times change in G bar, as before. So that gives you the intuitive story for why we get this magical multiplier process. Now diagrammatically, what does this look like? So again, we'll start with, we've got output on this axis, functions of output on this axis, and now we don't need to really draw the consumption function anymore. I'm going to focus actually on the aggregate expenditure function. So it has all of these components as before, as the autonomous components of aggregate expenditure. That's the intercept of this function. And it's got a slope of C1. And where this function cuts the 45-degree line, where z equals y, that's our initial equilibrium y star. Now, when we increase government expenditure, we can see that that's now a bigger intercept without changing the slope. So we got this, I've used red ink here for our new G bar prime. All it does is it shifts up the intercept of this function. So, but with the same slope, we're actually going to have a higher value of y that is the equilibrium y. Now, because there's a positive slope to this, this is saying that you'll notice that the change in y that we get out of this is bigger than the change in G bar. Right? That's because we got a positive slope C1. So let me just maybe, as an example, think, suppose C1 is equal to 0. Suppose consumption did not depend on income. Then this aggregate expenditure line would just be a horizontal line. And in that case, if that shifted up, then output would change only by exactly the same amount as G went up. But in general, that's not the case. So for every economy in the world, C1 is actually greater than 0. It tends to be somewhere, for example, 0.8 is a really standard, somewhere between, say, 0.75 and 0.85, very standard values for C1. So, given the fact that there is a marginal price to consume greater than 0, that then gives us our result, this multiplier result, that when you change any of the components of the exogenous components of aggregate expenditure, that will induce an increase in output greater than that initial change in the exogenous component. Okay, that's it for this lecture for this week. Next week we'll pick up from slide 51. I do want to say one thing about the assignment though. Assignment 1 may look a little bit complicated. It's very similar. It gives you a model that's very similar to the model that we looked at in the lecture notes. There are two differences. First of all, investment is actually now a function of income, and also taxes are a function of income, you'll see. However, the solution method for that model is precisely the same as the solution method in the lecture notes here. You start with z is equal to y, and then you plug in your z is equal to c plus I plus g, and then you plug in your components for c and for I and g, and you get one equation in y, and you solve that equation for y. That gives you your y star. So that's your starting point for that assignment. So good luck with that, and we'll see you next week.